Propositions can get more complicated when we start nesting quantifiers, that is, using several of them in succession. This video gives some examples. Take a moment to think about what these propositions mean. The symbol R means real numbers. The first proposition is saying that for all real numbers x and all real numbers y, x multiplied by y is the same thing as y multiplied by x. This is the commutative property for multiplication. The second proposition says that for all real numbers x, there exists a real number y such that x plus y equals 0. In other words, every real number x has an additive inverse. The order of my quantifiers is important here. If I wrote instead, there exists a y in R, such that for all x in R, x plus y equals 0, that would mean that there's a real number y, such that when I add any other real number to it, I always get 0. So that would not be true. Contrast that with the first proposition, the commutative property one. If I switched the order of quantifiers in that example, I'd still get the same meaning. It would still be true. The reason for the difference in behavior between these two examples is the first one, all the quantifiers are the same, whereas the second one mixes quantifiers. The third statement is also a familiar property of arithmetic. It says that for all real numbers x, y, and z, if I multiply x times y plus z, I get the same thing as x times y plus x times z. That's known as the distributive property. We've practiced going from symbols to words. Now let's go the other way and go from words to symbols. Let's write the following statements in logical symbols using U as the domain of students at UNC, M as the domain of math classes at UNC, T of xy as the propositional function x has taken math class y, and P of xy is the propositional function x has passed math class y. Please pause the video first and try your hand at doing the translations. The first statement, every student, that's a for all statement, for all x in U, taken at least one math class, that's an exist statement. There exists a math class such that the student has taken the math class, that's T of xy. In the second statement, there exists a student who's taken every math class. So for all math classes, the student has taken the math class. In the next example, there exists a UNC student, and they've passed all of their math classes. At first glance, I might try to code this as for all y in M, P of xy, but that's not correct, because that would be saying that there's a student who's passed all the math classes at UNC, and we just want them to have passed the ones that they've taken. So second try, I might write there exists a student such that for all math classes, T of xy and P of xy, but that's not correct either. That would mean that they'd taken and passed all the math classes that are offered at UNC. We're only saying that they've passed all the math classes that they've actually taken. In other words, for all students in all math classes, there exists a student such that for all math classes, if they've taken the math class, then they've passed it. This if-then construction is a handy way to limit the domain to the math classes that were taken. For the last example, some UNC student has failed at least one of their math classes at UNC. We're going to take failed to mean not passed. Once again, my first idea might be too simple. There exists an x in U such that there exists a y in M such that not P xy wouldn't be correct for a similar reason as before. We need to specify that they're not passing a math class that they actually took, not just some random math class that they didn't take. So I'm going to give you two possible choices, and I want you to decide which one is correct. Is it there exists an x in U there exists a y in M such that txy and not pxy? Is that it? Or is it there exists an x in U, there exists a y in M, txy implies not pxy? If you said the first one, you're correct. There's a student at UNC in a math class such that the student took the math class and didn't pass it. The second example does not represent the intended meaning of the sentence because it's saying that there exists a student in a math class such that if the student took the math class, then they didn't pass it. But that could be satisfied by picking some math class that they didn't take. Like say they didn't take number theory. Then it would be true that if they took number theory, then they didn't pass it because an implied statement is always true if the premise is false, right? But that wouldn't be the intended meaning of the statement. Just saying there's a student who didn't pass number theory because they didn't take it is different from saying that somebody actually failed a math class. If you notice that sentence C and sentence D had to be coded differently, you're right. Not only was there a difference in the second quantifier, but because of that difference, we ended up having to specify the fact that they took the class in two different ways. This video introduces the notion of nested quantifiers and touches on some of their subtleties, including the fact that the order of nested quantifiers can make a big difference when both the for all and the exist are included.